Hello students, welcome to the world of chemistry. This is Dr. Vikram Panchal and I'm dealing with wave mechanics for chemistry. And in this chapter, this is lecture number 10. In this lecture, I will explain you what is eigenfunction and eigenvalues. Okay, so in this chapter, we will discuss about eigenfunction and eigenvalues. So, eigen. It is a German word and in German language eigen means proper. So mathematically using a specific operator like differentiation, derivation. If a new function obtained with constant is the same as operand, then that function or operand is known as eigenfunction. And the constant is called eigenvalues. The equation is known as eigenequation. As for example, d by dx e raised to phi x. This equation is given here. D by dx is known as operator. This is e raised to phi x is known as eigenfunction. Why? Because the solution of this equation derivation is phi into e raised to phi x. So e raised to phi x is the same function like this eigenfunction. So the solution should have the same eigenfunction along with constant, and that constant phi is known as eigenvalue. So this whole equation is known as eigenequation. So this way, when any function is derived with d by dx, and if we get the same function as a solution with a constant, then that function becomes eigenfunction and the constant is known as eigenvalue. Okay, so consider the following expression in wave mechanics, that is d square psi upon dx square. This is equal to minus lambda into psi. Okay? Suppose this is the solution, then where lambda is independent of x. This is a simple second order differential equation. The general solution of the above equation in sine or cosine is given as follow, which is psi is equal to c cos under root lambda into x plus d sine under root lambda into x for lambda greater than 0. Now, in this case, under root lambda is a non-vanishing positive number and the general solution given by above equation is well behaved since it is continuous single valued and never increase to infinity. See, these are all conditions of Schrodinger's wave equation, because the magnitude of sine theta or cos theta always oscillates from +1 to -1. Okay, so psi, if for certain values of lambda, the operand psi is well behaved, then lambda is called the eigenvalue, sorry, lambda is called eigenvalue, yes, because it is a constant, and psi is known as eigenfunction of operator d square upon dx square. Okay, so this is the interpretation of this eigenfunctions and eigenoperator, or we can apply this to Schrodinger's wave equation. Now Schrodinger's wave equation is also written as Hamiltonian operator H psi is equal to E psi, where psi remains the psi, that means this eigenfunction. And here, what is operator? Operator is H, Hamiltonian operator, and for that eigenfunction will be psi. So what is eigenvalue then? In this case, eigenvalue will be E, because we are getting the same operand over here or same function over here. That is why E must be eigenvalue. And you know that a new function is again eigenfunction only. It should be the same like eigenfunction, and that is psi. Okay. So this is the interpretation of this. Similarly, d square upon dx square is an operator. And if e raised to x is eigenfunction, then 1 will be eigenvalue and e raised to x remain the same. So this way we can interpret this also. Similarly, suppose we take d square upon dx square with reference to sin x. So sin x become eigenfunction only when the new function is sin x. But here eigenvalue will be -1. Similarly, d square upon dx square, if we take sin ix, I is under root -1, then it will be +1, and again the function will be sin ix. Okay, d square upon dx square, if we take sin hx, so here it will be -h square as eigenvalue, and sin hx will be the new function. Follow? So this way we can have the same functions if we carry second degree differentiation, and that is also one of the important fact for us. Now we discuss here the new operator known as Hermitian operator. Hermitian operator. Okay. So here Hermitian operator is such that operator which obeys the eigenvalue equation. For example, a psi is equal to lambda psi, and operator A is said to be Hermitian operator if it satisfies the following conditions. That is, psi1 star a psi2 dt is equal to a psi1 psi2 dt.